Welcome to podcast 12.3c. Now, we have spent some time with the ideal gas law, and then we had the joy of gases and stoichiometry. And so now we're going to take it a little bit further and talk about some gas behavior. And this is stuff that you will have some real life examples with. For example, the property of diffusion of gases. Okay, what it is it's the movement of particles from a high area of concentration to a lower area of concentration. And the best way to think of this is perfume. Okay, someone put on a little perfume or some cologne, and or for me in the classroom, sometimes it's hand lotion. They'll put it on, and then those particles are flying around the room, and it's only a matter of time before people quite a ways away can smell it. And that's because the particles are just leaving in all sorts of directions. And as soon as one of them hits your nose, there you go. This is also, the reason why when someone farts in the room, oftentimes we'll smell it in a little while. Okay, same kind of thing. Gas is flying around. It's leaving this area of high concentration and spreading out. So that's diffusion. Now, fusion is a little bit different. This is the passage of gas under pressure through a tiny opening. Probably the best example that I could think of with this is a good old balloon. Okay, I mean, you think of it. You got this balloon, you got this really good note right there, but somehow in a few days your balloon is like this, and maybe even a few more days it's even like this. How is that possible with a balloon that's got a knot in the bottom of it? Well, it turns out that if we could look at the rubber at a very small level, okay, there would be these tiny little openings. Tiny little openings. So you can imagine gas particles are flying all over the place, whatever, right? And every once in a while, bing, one escapes out. Of course, times this by the billions upon billions of gas molecules that are floating around or flying around in that balloon. And after a while, enough have escape to where the pressure of the balloon is decreased and the volume of the balloon is decreased, and that's because the number of moles has decreased, right? So that's effusion. Now we're going to use a law, Graham's law of effusion, to calculate either the molar mass of a gas or how fast it will go. That's a pretty straightforward equation. And if you look at it, now you can look at the words here. The rate of effusion of a gas is inversely proportional to the square root of the gas's molar mass. Well, what does that mean in real life? Well, that means that the heavier, right? And when I say heavier, I mean the bigger molar mass, right? Grams per mole. So the heavier or the greater molar mass of a gas, the slower it's going to move. And hopefully that makes sense to you. A very light gas like hydrogen is going to move a lot quicker than a gas maybe like, I don't know, let's just talk sulfur dioxide or something. Okay, so that should make sense. So let's try a couple of these problems. You can see that the rate of 1 over the rate of 2 equals the molar mass of 1 over the molar mass of 2. And I do want to focus on this little cross relationship. See the 1's there and the 2's there? Because sometimes a student will put 1 on top and 2 on bottom, they'll get the wrong answer. So let's try one. So there's an equation. What's the rate of effusion for hydrogen gas compared to uranium hexafluoride? Okay, so we're trying to figure out this rate of hydrogen gas, right? So the rate of H2 over the rate of uranium hexafluoride, boy, that's kind of an interesting compound, UF6, right, equals the square root of the molar mass of 1 now, right? So what's the molar mass of H2 gas? Well, it's 2.016, right? And what's the molar mass of UF6? Well, if you were to calculate it out, which I have, 352.02 grams per mole, right? All right, so when I work that out, I divide those two, take the square root, I get a number that is basically 13.2, and that, of course, is over 1. So hydrogen will effuse at a rate about a little more than 13 times that of UF6, right? So that's one way to do another problem. And then here's a little more common way that we're going to find a problem. An unknown gas diffuses at a rate half that of oxygen gas. What is its molar mass? Okay, so I'm going to put this gas diffuses at a rate half of oxygen, right? So I'm going to put 1/2 on bottom and then 1, right, of the gas. And that's going to equal the square root of, now this gas is diffusing half as fast, right? So I'm going to make that my x down here, and of oxygen gas, and that's O2, right? So O2 weighs 32 grams per mole. Okay, so the first thing I'm going to do is I'm going to take the square of both sides, and that gives me 0.25, and that equals 32. I'm running out of room over x, right? Now, again, our awesome algebra skills will come into play. We'll put this x over here, and I'll bring this 25 under here, and I get x equals 128 grams per mole. Right? Now the question says, is that HBr or HI? Well, bromine weighs around 79 and iodine weighs about 126-ish. Okay, 79. So add 1 to that. So it's got to be HI. That's a little more common question, but you could say it's pretty simple math. Kind of interesting to see how fast these molecules are moving, and we'll do some rate problems a little later. Okay, almost done, guys. You guys are doing fantastic. We're just about there. We're on to the last little equation. That's Dalton's Law, partial pressures. You're going to love this law. Why? Because it involves very simple math. Look at this. The P total, anyways, it involves the math of just some addition. So imagine I've got this big cylinder, and then I've got some O2 and some H2 and some N2. And I've got a little dial on it, and the dial reads a certain pressure, right? Well, that pressure, that total pressure, is due to the individual pressures of O2, H2, and N2. So you can imagine a problem that might say, what's the total pressure of a cylinder with oxygen gas at 1.2 atmospheres, 3 atmospheres, and 1.8 atmospheres. Okay? So, the beauty of this equation is I just add them up, right? And I get 6.0 atms. So that's the total pressure. Not too bad, right? Probably your most favorite formula of this whole course. Now, how can we make this a little more challenging? Well, I could say, hey, a cylinder has a total of 10 atmospheres, and hydrogen has a pressure of 2 atmospheres, and nitrogen has a pressure of 5 atmospheres. What would be the pressure? What would be the pressure of O2? All right, and so there we would actually have to subtract, and so we would get 2 plus 5 is 7 minus 10. We would get 3 atmospheres is O2. All right. So there you have it, Dalton's Law of partial pressures. All the gases act independently of each other, and their pressure is due to just that gas itself. So there you have it. All right. This is the end of Chapter 12, guys. So if there are any questions, we will definitely talk about this in class next time, and we'll see you later.